Okay, so this video is going to pick up where the last one left off. We're giving another proof of the fact that the integral elements of a field form a ring over, say, some integral domain, and we're kind of following the proof. We're generalizing the proof that algebraic elements of a field form a ring, and we're trying to generalize these basically two key ingredients in that proof. So the first is a characterization of when an element is algebraic based on studying the field extension. Okay, the field extension joining the element. And the second condition is just a condition on extensions being the condition of a finite extension being transitive. Now, okay, so we basically successfully in the last one generalized this first condition. So the important proposition here is this guy. If A is an integral domain and L is a field containing this integral domain, an element alpha in L is integral over A if and only if there exists a non-zero finitely generated A submodule of L such that A sends this submodule to itself. Okay. So this is the important proposition that we're going to need this time around to kind of finish the proof of the result. Okay, so hopefully people have kind of internalized this if they haven't watched the last video. Okay. So the second condition, right, so let's say we wanted to prove what is the generalization of this second condition, right? It essentially says that, let's say, so it would say, instead of finite extension here, it would be like finite extension of what would this look like? This would look like, yeah, the second condition doesn't actually have a natural generalization. And the way we're actually going to prove the result is maybe not exactly generalizing the second condition. So the key proposition is as follows, essentially. Okay. Yeah, it's not exactly clear how this is a generalization of this second condition. So to prove integral elements form a ring, okay, we prove the following. Okay, so this is going to be the second key lemma. So proposition. Let alpha and beta is elements of the ring L be integral over A. We're going to let M and N be the associated modules from the previous proposition. So they're finitely generated A modules such that alpha M is contained in M and beta N is contained in N. And we're going to show that essentially then I can construct the module for alpha times beta or alpha plus beta. Okay. Then what do I want to say here? M times n, which is, maybe we'll do it on inline environment, m times n. So this is going to be another submodule of L. This is the set of all sums mi and I, such that, you know, mi is in m and ni is in n. Okay. So it's basically take all the products and make it a module, or make it an abelian group, really. Then this is a finitely generated A module. And what's more, you know, alpha plus beta times mn is contained in mn, and alpha times beta times mn is contained in mn. Okay. So, yeah. Okay. So, as you can see, this proposition is going to kind of immediately give us the desired result, because the aforementioned proposition is an if and only if. This is going to tell us that alpha plus beta and alpha times beta are both integral over A. Okay. So there are two. So let's go ahead and get to the proof of this. There are two kind of pieces to this. I guess maybe three, but the second piece is kind of, I don't know, they're pretty much the same argument. Proof 1, we need to show that mn is finitely generated. I guess 2a, we need to show that alpha plus beta mn is contained in mn, and 2b, we need to show that alpha times beta mn is contained in mn. Okay, so I guess the only one you really have to do any thinking about, I guess, is mn, or the first one. The second two being like kind of just following from the definitions. So let's think about the first one. And again, I'm not going to go through. Well, actually, yeah, maybe since this video is already going to be so short, I can actually go through the proof here. I'm just going to let I equals 1 to little m, and let's say I equals 1 to little n. Let's say these generate m and n respectively. Okay. And then we're going to kind of consider the obvious, or like the natural choice. I claim, if I just take the product, vi uj, 1 less than or equal to I, less than or equal to m, 1 less than or equal to j, less than or equal to n. I claim this generates m times n. Okay, so how do I prove this? Well, I guess we can see that every element can be written as a sum of these products. Okay, so really I just need to show that each of these products can be written in these forms. Okay, so it suffices to show each product let's say I'm going to use alpha in M and beta in N. Alpha and beta are not the right. Let's do, I can't use M and N either. So let's do, I guess I could use A and B. So let's do A and M and B and N is in the A module generated by this basis, the IUJ. Okay. So, I mean, you kind of do the natural thing. You say, okay, A is an M, so it's got to look something like, let's say, CI, VI, with the CI is an A. B is going to be, let's say, DI, UI, where the CIs are in, the CIs and the DIs are in A. Then you just take the product and expand it out. A times B is the sum of the CI VIs, and this is the sum of the DI UIs, and then it's going to be the sum of the CI DJ VI UJ, where 1 less than equal to I less than equal to M, 1 less equal to J less than equal to N. Okay. And, you know, these guys, this coefficient is an A, these guys are elements of the basis, and so it works out. Okay. So, we've shown that M times N is finitely generated. I see. Now, these conditions 2A and 2B are like very easy to check. So, to check 2A, B, simply check on an element. I guess maybe I won't even say that. I'll say to check 2AB, use that alpha M is contained in M and beta N is contained in N. Okay. So I'm not going to go through that. It should be, if you've understood everything up until now, this should be very easy. I guess, yeah, corollary. So the corollary is as follows. Let A, corollary is the main result that we want. Let A be contained in L, L a field, A an integral domain, then the elements of L integral over A form a ring. And the proof basically use first proposition, second proposition, and then first again. So the first proposition gives me such an m and n. Gives me an m and m satisfying the hypotheses of the second proposition. This one here. Okay. Then, so that's what I mean when I say use first proposition. And the second proposition tells me that this product, m times n, is a finitely generated submodule such that the sum and the product take this finitely generated submodule into itself. And then the the first proposition again tells me that this is a sufficient condition for these two things to be integral over A. So, and again, if you want to flesh this out, which I do recommend you do, yeah, basically if this is confusing to you, you should sit down and try to flesh this out. Okay. So I want to make some closing remarks on this proof. So the first one I want to make is basically that I want to draw some parallels to argue that this really is very similar to the proof in the case of fields. Okay. So remarks. Okay. So I guess the first thing I want to say is that, if this A, so pretend A is no longer an integral domain, but is actually a field, I guess the case for fields is actually like a special case of this. So if A is a field, then algebraic over A really means the same thing as integral over A. These two words don't mean anything different in the case of fields. This is because, basically, in integral, you have this additional adjective monic. But if you're over a field, you can just divide out by the leading coefficient. So if I'm algebraic and I have a minimal polynomial, I can divide out by the leading coefficient and just assume that that polynomial is monic, giving me something integral over A. Okay. The second thing I want to draw is okay, so in what way, I guess the question that arises to me is I guess there are several questions. So, questions. So what are my questions? One of them is, when I talked about this proposition in the last video, I stated this proposition like this, and then I gave this more natural corollary. An element alpha in L is integral if and only if A join alpha is a finitely generated A module. And this corollary is more natural to state, but let's think about what would happen if all I had was this corollary and I didn't quite have this proposition. Okay. So I guess the question is, why not just use the corollary, the more natural? Of what I'm calling proposition 1 here. Okay. And so let's think about what that would look like. So this will be a little bit more informal. So I would know, A join alpha and A join beta are finitely generated A modules. Or, yeah, finitely generated A modules. I know these are finitely generated A modules. What I need to know is, how does this imply that A join alpha beta and A join alpha plus beta? I need to now know that these are finitely generated A modules. And I think actually, maybe I don't actually have a good answer for this question, because I think, so this is, Well, I guess, okay, so the first one is, this is now A join alpha times A join beta. Okay. So this, is that true? Oh, no, sorry, yeah, no, this is not true. This is not A join alpha times A join beta. I lied. So I think that's the main issue, right? This is only a submodule of this. Because, okay, so why is this not equal to this? I have something, here I have something like alpha times beta squared. But here, the power of alpha and the power of beta have to actually be the same. Okay? Or like, I mean, even simpler. This, so, in A join alpha times A join beta, I just have alpha because I've got 1 on the right hand side here. But in this guy, I don't actually just have alpha. The power of alpha and beta have to be the same. And I need to know something like, right, I know this guy is finitely generated. Okay, and I know that A join, yeah, I know that A join alpha times beta is finitely generated by an argument like this, so I could have made this argument about A join alpha times A join beta. But then I would need to know that the submodule A join alpha times beta is also finitely generated. And I mean, in general, you need some kind of Noetherian hypothesis on these things. Like, in general, it's not true that the submodule of a finitely generated module is finitely generated. Okay? So there's some more work to do if you do it this way. Okay. So that maybe answer A join alpha times beta is properly contained in A join alpha times A join beta. You need to show, I guess, the fact that A join alpha times A join beta is a finitely generated A module. Does, at least not that I can see, not immediately. I'm sure there is an argument that works like this, but this argument is the one that Milne gives, and it's easy for me to follow. So the fact that A join alpha times A join beta is a finitely generated A module does not immediately imply that A join alpha times beta is as well. Okay, and I think you run into a similar problem with this guy sitting properly inside A join alpha plus A join beta. Maybe it doesn't sit. Oh, probably it often sits properly inside here. Yeah. Okay. So, regardless, you run into issues like this. Yeah, that don't, at first glance, I don't know how to circumvent them. So that's why we use this like slightly more general proposition that ends up being useful. Okay, and the other question I want to return to is basically to notice that, you know, this proof here is very similar to the proof for fields. Like, to show what do I want to say here? Like, you need to show, like, to construct a basis for, so let's go up to proposition 2 for fields. So the basically the property of being a finite extension is transitive. Basically, the way this argument works is you take a basis for m over L and a basis for k over m, and the basis for k over L is just like the product of the basis elements. Okay. So again, you have two bases and you take the product. So they are very similar arguments. Okay. Okay, so that pretty much wraps up this section. I've given so far two proofs that the ring of integers in an integral domain is actually a ring. So from now on, I guess maybe just a definition. Let A be Z, and I don't know, L a finite extension of Q, we call the elements of L integral over A the ring of integers and denote it by this math cal O sub L. Okay. And by and large, the goal of almost this entire course and of most of algebraic number theory is basically studying O sub L, so this generalization of Z, and kind of, saying certain things about it.